Hello everyone. In this video, we are going to see three-phase semiconductor fed DC separately excited motor. The three-phase semiconductor is a one-quarter converter. So with this converter, we will be able to get only one mode of operation, that is forward motoring mode of operation. The armature of the motor is fed from the three-phase semiconductor, and the field winding is given a constant DC source. The variable output voltage from the three-phase converter will feed a variable armature voltage so that we will be able to get the speed control. The method of speed control, by this method, it is nothing but the armature voltage control method. There are two modes of operation, continuous conduction mode and discontinuous conduction mode. In continuous conduction mode, armature current never becomes zero. The devices are numbered in which they are triggered. Initially, T1 will be triggered. After 120 degree interval, T3 will be triggered. And after again 120 degree, T5 will be triggered. Each device will conduct for 120 degree duration. When T1 is triggered, it will conduct along with the already conducting device, that is T6, and the armature is connected between A and B terminals so that VA will be equal to VAB. And after 90 degree, T6 will be turned on off automatically, and so T1 will conduct along with T2 so that VA will be equal to VAC. When T3 is triggered after 120 degree, it will conduct along with T2, and again after some time, it will conduct along with D4. For firing angle equal to 60 degree and above, VA is only equal to VAC after T1 is triggered, because at that time, D6 would have already turned off. So the phase voltages are indicated by VAN, VBN, and VCN. VAN is taken as reference. The equations for VAN, VBN, and VCN are given here. The corresponding line voltages VAB, VBC, and VCA are also given here. Now, when we are going to take the VM as √3 times VMP, where VMP is the peak value of the phase voltage. Now we can see that your VAN, VBN, and VCN are drawn here. T1 will be forward bias whenever VAN is more positive. T3 is forward bias when VBN is more positive, and T5 is forward bias when VCN is more positive. Similarly, when VAN is more negative, T4 will be forward biased. When VCN is more negative, D2 will be forward biased, and when VBN is more negative, D6 will be forward biased. The output voltage waveform, as we already saw, it follows only the line voltage waveform. So the line voltages are considered for drawing the armature voltage. Now, the line voltages are drawn with VAB, VBC, and VCA. Since the line voltages are drawn in positive side only, because we will be getting only the positive side voltage when in the semiconductor. So all the line voltages, that is VAB, is drawn here. The VAB, the negative part of the VAB is drawn in the positive side itself with the VBA. Similarly, BC and VCB are drawn, and VAC and VCA are drawn. So when the waveform which is shown here is the armature voltage waveform, that the black colored waveform, it is the armature voltage waveform. This waveform is drawn for alpha equal to 60 degree. So when alpha is equal to 60 degree, as we already saw that when T1 is triggered, it will conduct only with D2, because already D6 would have been turned off. D6 would have been turned off. So when we trigger at alpha equal to 60 degree, when we trigger T1 and D2 combination will conduct. So the output voltage, that is armature voltage, will be equal to VAC waveform. This is VAC waveform. So VA will be equal to VAC waveform until T3 is triggered. When T3 is triggered, the armature voltage will be equal to VBA waveform. And when T5 is triggered, T5 and D6 combination will conduct. So the armature voltage will follow VCB waveform. And the armature current, it is always greater than 0. So armature current will be having the shape like this. So this is for alpha equal to 60 degree. The average output voltage can be found by integrating the output voltage waveform between pi by 6 plus alpha, where pi by 6 is the natural point of triggering. The next point of triggering is pi by 6 plus alpha plus 120 degree, that is 2 pi by 3. So if we integrate VA over this period, we will be able to get the average output voltage or average armature voltage. So VA will be equal to 3 by 2 pi integration between pi by 6 plus alpha to pi by 6 plus alpha plus 2 pi by 3 VA d omega t. Now we can see that from this waveform, during that time, the armature voltage, it follows VAC waveform. So we have to integrate this between pi by 6 plus alpha 2, and we can also see here that at this point when T3 is triggered, this is the time that is pi by 6 plus alpha plus 2 pi by 3. So this point is nothing but 7 pi by 6, because this is pi by 6, this is 2 pi by 6, 3 pi by 6, 4 pi by 6, 5 pi by 6, 6 pi by 6, and 7 pi by 6. So instead of pi by 6 plus alpha plus 2 pi by 3, we can write 7 pi by 6. So if we integrate VAC between the lower limit pi by 6 plus alpha to upper limit 7 pi by 6 alpha, we will be getting the average armature voltage, that is VA. So after and VAC, we can write it as minus VCA. VCA is given here as, here it is given that VCA is Vm sine omega t plus 5 pi by 6. So substituting for VCA here, substituting for VCA here and integrating, we will get VA equal to 3 Vm by 2 pi cos omega t plus 5 pi by 6. This is the integration, and we have to substitute the limits as pi by 6 plus alpha to 7 pi by 6. Substituting the upper and the lower limits and simplifying, we will get the final average armature voltage VA equal to 3 Vm by 2 pi into 1 plus cos alpha. And we need to substitute this VA in the speed torque equation of the DC separately excited motor. We know that the speed torque equation is given as omega m is equal to VA by K minus TRA by K square. Okay, now if we substitute for VA, we will get omega m equal to 3 Vm by 2 pi K into 1 plus cos alpha minus TRA by K square. This is the speed torque equation of DC separately excited motor fed by three-phase semiconductor in continuous conduction mode. The characteristics for this speed torque equation will be of this form. Okay, so by varying the firing angle, we will be able to get the series of speed torque characteristics, which will be of parallel lines. This line will be for alpha value, which is greater than, if, for example, if this is the characteristic obtained for alpha 1, and if this is the characteristic obtained for alpha 2, and if this is the characteristic obtained for alpha 3, then alpha 3 will be more when compared to alpha 2, which will be more when compared to alpha 1. So which means that alpha 1 is less than alpha 2, which is less than alpha 3. Okay, so this is a speed torque characteristic for continuous conduction mode. Now we can obtain the speed torque characteristic for discontinuous. Now we can obtain the speed torque characteristic for discontinuous conduction mode. Here we know that the armature current will not be always greater than 0. It is not continuous. So it reaches 0 before the next device of the converter is triggered. Okay, when there is the armature current, VA follows the line voltage as before. At omega t equal to beta, the armature current reaches 0. From beta to the next instant of triggering, will not have any armature current, and which means that there will not be any device in conduction mode. Hence, the armature is disconnected from the source. Hence, the armature voltage will be equal to the back EMF. So the waveforms for discontinuous conduction mode for alpha equal to 60 degree are drawn here. So when T1 is triggered, at that time, that is pi by 6 plus alpha, during that time, the armature current is not having any value. It is starting from 0. So at pi by 6 plus alpha, the armature current will rise from 0, and it reaches 0 at beta before the next device, that is pi by 6 plus alpha plus 2 pi by 3. We are going to trigger the next device T3. Before that, the armature current reaches 0 at beta. Okay, so from pi by 6 plus alpha to beta, T1 will be conducting along with T2. So at that time, the voltage will follow VAC waveform. Okay, now from beta to next instant of triggering, that is pi by 6 plus alpha plus 2 pi by 3. Since the armature current is 0, there is no any device conducting. At that time, the VA value will be equal to the back EMF. Okay, so back EMF line is shown here. Again, from pi by 6 plus alpha plus 2 pi by 3 to beta plus 2 pi by 3. T3 and T4 combination will conduct. At that time, the armature voltage will follow VBA waveform. And from this instant, beta plus 2 pi by 3 to next instant of triggering, no device is on. So the armature voltage is equal to the back EMF. Okay, so this is going to be the darkened portion, that is black line shows the output voltage or the armature voltage waveform. Okay, now we have to find the average value of the armature voltage waveform by integrating this waveform. Okay, so since there are 3 pulses per cycle, we are going to have 3 by 2 pi. Integration from pi by 6 plus alpha to pi by 6 plus alpha plus 2 pi by 3 VA d omega t. Now, this integration can be split into 2 parts because from pi by 6 plus alpha to beta, the waveform, it follows VAC waveform. From beta to this instant, the waveform follows E waveform. So we can split the integration into 2 parts. Pi by 6 plus alpha to beta, the voltage is equal to VAC. From beta to 5 pi by 6 plus alpha, the voltage will be equal to E. Okay, so now if we integrate and substitute the lower and the upper limits, and after substituting the limits, we will be getting the final armature average armature voltage as VA equal to 3 by 2 pi Vm cos 5 pi by 6 plus alpha, cos 5 pi by 6 plus beta plus cos alpha plus E into 5 pi by 6 plus alpha minus beta. So this is the average armature voltage. Okay, now we need to substitute this voltage in the speed torque equation in place of VA. Okay, if we substitute that, we will be having the relation like this. In the speed torque equation, we should have only omega m and t. We should not have E because E is again a function of omega m. So substituting E equal to K into omega m. We know that E is equal to K into omega m. And again, rearranging, we will get the speed torque equation as given by this this equation. That is omega m equal to 3 by 2 pi Vm cos 5 pi by 6 plus beta plus cos alpha divided by K into 1 minus 3 by 2 pi 5 pi by 6 plus alpha minus beta minus TRA by K square 1 minus 3 by 2 pi 5 pi by 6 plus alpha minus beta. This is the final omega, that is speed torque equation in the discontinuous conduction mode. Now, if we draw the above equation, we draw the characteristic by considering this equation, we will be getting the characteristic which is given by this graph. Okay, this graph shows the speed torque characteristics for including the continuous and the discontinuous conduction mode. This is the boundary line which separates the discontinuous mode with the continuous mode. Okay, so right hand side of this boundary line will be for continuous conduction mode, and the left hand side of this line will be for discontinuous conduction mode. Okay, so this is the speed torque characteristic for discontinuous conduction mode, and this is the speed torque characteristic for continuous conduction mode. Okay, so this is the combined speed torque characteristic for continuous and discontinuous conduction mode. Okay, so in this video, we have seen the three-phase semi-converter fed DC separately excited motor, both for continuous and the discontinuous conduction mode. We have drawn this beta characteristic for continuous and discontinuous conduction mode. Thank you.